Hello, Stats 300, and this is Professor Gonzalez. And I would like to go over some of the homework or the homework questions on the assignment side. The assignment side from sections 9.1. And I've noticed people have started looking at the videos and the classwork, optional classwork sheets to go along with that. Of course, the classwork sheets are in Canvas just like they were before. The assignments for the videos, circling which ones to look at, are also in Canvas, and I noticed people have started that. That's great. You should be looking at that by now, but I wanted to kind of circle around and do some of the problems in 9.1 and 9.2 for you, just to maybe tie it back and look to our problems here. Anyhow, I think I would like to start off by just talking a little bit about this topic, which is taking a look at hypothesis testing. In this particular section, 9.1, we're not actually doing a full-blown hypothesis test on the assignment side of 9.1, but we will do some in 9.2. But let me kind of get some of my thoughts about this and maybe try to tie some of this together with some notes down here. So let me start right here. Let's say that that we're talking about the average or the mean population height of males in the United States. Let's just say that. So let's say we actually knew that the population mean of the height of adult males in the United States is 5 feet 9 inches. So that would be 69 inches. And so let's say that someone was doing a study and they were kind of starting to challenge that. They were saying, let's say that someone challenged that and said, I think that the mean height of adult males in the United States is greater than 69 inches. So we've set up this whole thing about this hypothesis testing. So this, and I'm going to get into some more of the details in this particular homework set, but this H sub 0 or H null, or the null hypothesis, is always going to have some kind of equality with it. It's always going to have an equal signs or a less than or equal or greater than or equal. Some books like to do it that way, but it will always have some sort of equal sign involved, and that's our assumption. So that's basically what the population mean is. So we're going to assume that the population mean is 69 inches, and that's what it said. That's what they told us. They told us the population mean is 69 inches. So the average height of males in the United States is 69 inches. Now our alternate hypothesis will be shown as H sub 1, and that's another alternate hypothesis, and that would be, I think that the mean height of adult males in the United States is greater than 69 inches. So what happens here is when we do a full-blown hypothesis test, of course this has to be for a normally distributed population, and here we have our mean right there, which was 69 inches. And then we take, we do some sampling, simple random sample. We want those samples to be greater than 30. And, must be greater than 30 if it's not from a normally distributed population. Anyhow, from our samples, we're able to get our sample mean, or X bar. And using the sample mean, or the X bars, we're able to use a test statistic, and of course we'll have to do that in 9.2, but that test statistic comes from a formula that'll give us, depending on which problems we're doing, it could be a t-value, it could be an a t-value, it could be a z-value. But anyhow, there's going to be a formula that's going to give us this test statistic. Okay, so anyhow, but more importantly, basically what's happening here is if I take, I think I want to forget about that part for right now because I'll go into more detail of that next section. But if I was taking sample mean, wouldn't that be like the next best thing, right? If I was wondering if my mean population was actually 69 inches, one way to do that is to get a simple random sample of, maybe let's say 100 adult males, and we just try to do this simple random sample. And it turns out when we do that, my sample mean, this X bar, ends up being, let's say, 71 inches tall, right? You could also do another sample that maybe it's below, maybe it's down here, and it's less than. Um, but I guess what I'm saying is we're kind of expecting it to not be exactly 69, because it's a sample. So for it to actually be exactly that is a little bit hard to believe. Now, if you did a bunch of them and you found the mean of those sample means, we know from the central limit theorem that will be actually the same thing. But really what we're looking for here is something a little bit different. We're basically saying, so remember what is unusual in statistics? Just generally what's unusual in statistics is when we have, what percentage? 5%, right? We say when something is 5%, it's typically unusual, and that doesn't have to be 5%. That's just kind of a common place to look at. But I guess what I'm I keep on saying that, but what I'm saying is if our sample mean was bigger than 69, like what is big enough for us to say, you know what, I think I'm gonna reject 69 as the mean because I've got so much evidence. I've got enough evidence that tells me it's bigger than 69, okay? And at what point do we just say, I can't reject it? And so that level to reject comes from this idea, in this case, we have 5%. So essentially what's going to happen when we do our hypothesis testing is we're going to use our test statistic, which is measuring these sample means. And it turns out if we end up through sampling with our test statistic being in this highly unusual place, then what we're going to do is we're going to reject that null hypothesis. So, this is our cutoff right here. So, if our test statistic ended up being, let's say, not in our cutoff red unusual zone, then we'd say, okay, we're not going to reject this statement. And by the way, the closer we are, when we're looking at data, the closer we are to this mean, the more we feel like that mean is probably an accurate statement. We're saying that the mean, the average or the mean height of adult males in the United States is 69 inches. Well, if we did sampling and it turns out, that every time we sampled our test statistic put us like right close to the mean, would say, I think that's probably pretty good. But if our test statistic put us, let's say way, into this highly unusual area of 5% or maybe 2% or whatever the cutoff is. See, so there will be a cutoff. We'll have to know what that number is. But if we get into that region which is highly unusual or unusual, then we're gonna say, well, this is unusual, and because that's unusual, I'm going to reject that null hypothesis, which means I'm going to go with the alternate hypothesis. And that's kind of what's going on here. So really, the further away from the mean to the right, the more we want to reject. Or if we're going to say, what if they say, what if someone said, I think that the average height of adult males is less, they're getting shorter. Well, then in order to reject, in that case, we'd want it to be further from the mean, and then you would reject. So if we were way down here, you might reject down there. But if you were sampling, your sample mean and test statistic end up being close to the mean, well, then you wouldn't reject because it's going with what your initial statement was, and that would be that the average height of adult males is 69 inches. But once again, if it's further away from the mean, it gets into this unusual region of our population, which means we start questioning it, and that means at some level, whatever we set it to be, we reject the null hypothesis. So that's what's going on. Right now in this particular section, we're just learning how to figure out how to reject, let's see, we're trying to figure out what the null hypothesis is compared to the alternate hypothesis, and also different types of errors, type 1 and type 2 and things like that. So let's take a look at what we're actually doing. Hopefully that gave us a little bit of background, and we'll get more into that on the next section. Question number 1. Right away we're talking about type 1 errors and type 2 errors. Okay, so I'm going to spell that out for you. But man, I thought I got away from this. Now I'm going to go back to this example already again. And all of this is giving us like good solid data to reject. Once again, if I do all these I do my sample means, and it turns out with my test statistic, it puts me in this unusual region. That gives me enough information to reject that null hypothesis, meaning I'm going to go with the alternate hypothesis. I still might be wrong though. That's the thing. I might be wrong, but this gives me a lot of statistical information to statistically make that claim. Okay, and I feel like by using the statistics, it makes me much more likely to be correct. But still, an error can happen, right? An error can happen. And by the way, if we want to be more accurate, we can make this number, instead of saying unusual at 5%, we can say, like highly unusual, and make this little tiny bit the region that we reject at maybe 0.01. So we'd have to be way off of the mean to be in this rejection region way down there. Okay, but we still can be wrong. What if our sampling was wrong? We sampled incorrectly, or we just were super unlucky or whatever, and we accidentally sampled all these guys from the Olympic basketball team, and now we have we have all these data points that are way up there, so we figure that we're wrong, but actually it was 69 inches, right? So we can be wrong. And so there are two different types of errors that we like to classify when we're wrong. A lot of times we get it right, but sometimes we actually can get it wrong. And so let's just see what they're talking about. And let me spell this out a little bit. Let me go with some red here. And I'm going to say that a type 1 error. So what is a type 1 error? A type 1 error is when you reject the null hypothesis, even though, even though it's true. So you rejected, so basically what you do, you rejected something that was true. That's an error. And I don't have a whole lot of space here. What is a type 2 error? Type 2 error is when you fail to reject. So you don't reject the HO even though it's false. So see the difference? They're both an error. They're both an error, type 1 error. You're rejecting the null when it's true. And type 2 error is you fail to reject. You do not reject HO when it's false. You let it slip by. You didn't reject it, but it was a false statement. Once again, type 1 error, reject HO even though it's true. Type 2 error, fail to reject when it's false. Okay, so let's see what's going on here. It says a company that manufactures steel wires guarantees that the mean breaking strength in kilonewtons of the wires is greater than 50. They measure the strengths from a sample of wires and test the null, HO, and we say that it is equal to 50 versus its alternate says that it's the mean breaking point is greater than 50. All right, that sounds good. And notice you're going to find out the more we do these that the null will always have an equal sign involved, some type of equality, and the alternate will always have something that's not equal, so greater than, less than, even possibly a not equal symbol. That's not appropriate in this problem. So if a type 2 error is made, which is rejecting the null even though it's true, is made, what conclusion will be drawn regarding to the mean breaking strength? Okay, the conclusion will be that the mean breaking strength is greater than 50. Or we can just use a greater than symbol. Right? The conclusion, so if we do a type 1 error, we would reject this even if it was true. So if we rejected this, we would say, right, once you reject the null, you go with the alternate. So that means you have to go with that the mean is greater than 50, and so that's why we got that. Okay. All right, what about the next one? And the next one says a type 2 error is made. Now what is a type 2 error again? A type 2 error, let's just look up here. A type 2 error is when we fail to reject the null even though it's false. So a type 2 error is made. What conclusion will be drawn regarding the mean break? So if we fail to reject the null, that means we would go with it, right? So we fail to reject that even though it's false. So that would be, whoops, I just lost, there we go. That would be that mu equals 50. Mu is equal. This thing is freaking out on me. Okay, wait, there we go. Mu is equal. It's really, it's frozen. Come on. Somehow I got it to unfreeze before. There we go. Let me see if I can actually just write equal. I'm trying to say equal. Okay, so we're trying to say that the conclusion will be that the mean breaking strength is equal to 50. Once again, that's because we failed to reject, so that means we had to take that. Okay, next question. It says, the test uses a one-tailed alternative hypothesis. Explain why a one-tailed hypothesis is more appropriate than a two-tailed hypothesis in this situation. Well, this is probably a good time for me to explain one-tailed and two-tailed hypotheses. So I think I'll do that. So I'm going to get down to some space, a place where I have a little bit of space here to work with. And I think that's going to be right about here. So first of all, when we're coming up with our hypotheses, the first one we like to put down is called the null hypothesis. So we come up with the null hypothesis, and the variable or the symbol for that is just going to be h sub 0. Okay, the null hypothesis will always have some sort of equality, and some books like to just use equal, and some books like to use less than or equal, greater than or equal, but the main point is that they will have this equal piece to it, okay? With the null hypothesis, it will have that equal piece to it. That is probably the easy one, and also it's usually the population mean or the existing thing we already know. Okay, and then the alternate or alternate hypothesis is, the symbol we use for that is H sub 1, which is the alternate or alternative, and the symbols we use for that would be not equal, or less than, or greater than. But there is not going to be any equality involved in this statement. Not equal, less than, or greater than. Okay, so those are the three possibilities. And from those three possibilities tells us the type of test we're going to do. So you always look at the alternate to see what kind of test we're going to do here in terms of the tails. Let me see if I can draw it out for you. We've got three possibilities. We've got number one, if in this case mu is greater than, we're using the greater than symbol. If mu is greater than, and remember we're talking about the alternate hypothesis. So if it's greater than whatever, let's see, what does our picture look like here? It looks something like this. We've got the mu there. What's greater than mu? See, it says greater than. Well, that's to the right, isn't it? And since it's to the right, so whenever the alternate hypothesis shows a greater than symbol like this, we know this is going to be called a right-tailed test is what we're going to do. Okay, well, okay, number two. So that's greater than. What if the alternate hypothesis says mu is less than something? What does that picture look like? Well, that would be, there's our normal distribution. There's our mean, our mu. If it's less than, it's not supposed to be equal to, so let me get rid of that just in case it looks like equal to. If it is less than, that means it's to the left, which means we're talking about, you know, what test are we going to use? It's going to be a left-tailed test. Okay, and then the last option is this one right here. Number three. What if the mu was not, what if it's not equal to whatever we're talking about? What does that picture look like? Well, that looks like something like this, where we've got the mu, right? And it's not equal to it. So that means it could be less than or greater than, right? It could be less than or greater than. So we have to test both sides. We have to test it down below, and we have to, because it could be less than or it could be greater than. So we'd have to test the right side and the left side. And so that's why this is called tail here and a tail here. It's called two-tailed. Okay, so that gives you how you find if it's right-tailed, left-tailed, or two-tailed. Once again, if your alternate hypothesis has a greater than symbol, it's going to be right-tailed. If it's going to be a left-than symbol, it's going to be a left-tailed. And if it's a less than symbol, rather, it's going to be left-tailed. And if the symbol is not equal to it, mu is not equal, it's going to be two-tailed. Okay, let's go back to our problem. I believe it's right here. So this is part 3 of 3. We're still on the first question. It says this test uses one-tailed alternative hypothesis. Okay, explain why a one-tailed hypothesis is more appropriate than a two-tailed situation. Well, first of all, when we go up here, we can tell because look at that alternative hypothesis is greater than. There's your greater than symbol. So if we're kind of trying to visualize this stuff again, our test would look something like this. They're telling us that the the mean breaking point is at 50, and we want to know when it's greater than 50. So when you do your sampling, it could be if it's somewhere in here and it's reasonably close to mu, the mean, I'm going to accept that hypothesis, that null hypothesis, that it's equal to the mu or the mean is equal to 50. However, if it gets, way up into this unusual region, I'm going to reject it. So that's why I got to make this a right-tailed test is appropriate for this problem. So that's kind of what they're asking. So which one is, why is a one-tailed? Because, let's see, so it's a one-tailed, let's see, I got to answer it. With a one-tailed hypothesis, we can conclude that the mean breaking strength is greater than, so that's why it's going to have to be that. It's going to be greater than. Because it's to the right, greater than. Why is it not a two-tailed? Well, with a two-tailed test, we will know whether the mean breaking strength is less than or greater than. Less than or greater than. We don't want to know if it's less than or greater than, right? A two-tailed test would tell us if it's greater than that mean or if it's less than. We don't want to know greater than, less than. We want to know if it's greater than. So that's why the two-tailed is not appropriate for that problem. Next problem, number 2. Determine whether the alternate hypothesis is left-tailed, right-tailed, or two-tailed. This should go pretty quick. Okay, what do we focus in on to try to figure out the tail? We don't look at the null, we look at the alternate hypothesis. And because it's greater than, and I think you probably can already see it, but I'm going to draw it anyways. There's my mu, which would be, in this case, 29. We want to know, by looking at data, can we determine if it's greater than 29? And the only kind of test that's going to do that is to the right. So therefore, this is going to have to be a right. So the answer down here is right-tailed. The alternate hypothesis is right-tailed. Okay, determine whether the alternate hypothesis is left-tailed. Okay, same thing. Okay, now this one, it is not equal to 18. So let's draw that picture. Once again, you don't have to draw these, but when you're, I think, kind of locks it in a little better. There's our mu at 18. That's our null hypothesis. When we want to check data and see if it's not 18. So we want to test both sides. We want to see it might be greater than, and that would be if it's way up here. It might be less than. So that might be so we got to test both sides of that, and so that's going to be a two-tailed test, or two-tailed. All right, let's see. Next question. Back to type 1 and type 2 errors. Determine whether the outcome is a type 1 or type 2 error. Well, let's take some notes again. A type 1 error is when we reject the null when it's true. So you're rejecting something that's true. That's definitely an error, and that's called a type 1 error. And then what is a type 2 error? Well, type 2 error is when you fail. You don't reject. You fail to reject the null. You don't reject it. When it's false. So type 2 error is when you fail to reject when it's false, in a way accepting a false thing. All right, so we want to know what's going on here. A test is made. The null says mu is equal to 50, and the alternate says that mu is less than 50. Okay, maybe we get a little picture going here. As you know by now, I'm kind of a picture freak. So here is my alternate, here is my normal distribution. It says that our Our null hypothesis says that the mean is 50, and we want to see our test really, right? So our alternate hypothesis is less than 50. So basically we want to test, this is going to be a left-tailed test is what we're looking for. And now it says the true value of mu is 47. And what did we do? So the true value is that it's less than, so it actually is less than, and we reject it. So basically what happened here, we, let's see, it says the null is rejected, so we rejected the null, and we go with the alternate hypothesis. It says that mu is less than 50, and it actually is less than 50. So this is not an error. This is a correct decision. This is a correct decision. Kind of, we thought it had to be an error, but it's not an error. We did it, called it right there. All right, so this is how a problem starts really, but they're just asking us, I believe, just to set up the hypothesis, the null hypothesis and the alternate hypothesis. All right, let's see what it is. A fertilizer, so we got fertilizer. A new type of fertilizer is being tested on a plot of land in an orange grove to see whether it increases the amount of fruit produced. The mean number of pounds of fruit, so the mean number of pounds of fruit on this plot of land with the old fertilizer is 399 pounds. So that is our mu. Okay, and then what happens? Agricultural scientists believe that the new fertilizer may change the yield. Okay, now be careful. It says may change the yield. It didn't say it would make the yield greater. It didn't say it would make the yield less than. So if it was less than, you'd use, less than, greater than, right-tailed test. But it says change, and change means not equal to it. So for our first part, our null hypothesis, as you probably can see, remember it has to have the equal sign in it, so it's going to be the mu equals 399. And then our alternate hypothesis is going to need to use this, let's see if the fertilizer changes the yield, and changing means it's not equal to 399. So that we would test that and see if mu is not equal to 399. Once again, the reason why it would have to say something like, agricultural scientists believe that the new fertilizer may increase the yield. And in that case, you'd say mu is greater than 399, right? But that's not what they said. They said change, and change is going to be not equal to it. Okay, I hope that helps and gets you started. If you got stuck on the assignment side of ALEKS on 9.1, hopefully that gets you unstuck and you can knock that out and get it going. I'm going to kick out another one. And also, I've been kind of playing around with the ALEKS calculator, and we haven't really used the calculator much in the past. I am open for you using the calculator now that we've used our tables and things like that. I called tech support and I looked all over the place to see what was going on, but they let me know that I cannot just automatically open up the calculator. So ALEKS gives you access to the calculator on certain problems and doesn't give you access on other problems. And so at this point in the semester, I'm ready to let you use it anytime you want, but I cannot just automatically open it up all the time because it won't let me. So I'm trying to figure out different ways of getting around that, but I'm kind of stuck a little bit, but I'm trying. By the way, we can also do this with tables, and that's not a problem because that's what a lot of times most books intend for you, just to use a table. And I'll show you how to use the tables just like we've been doing before with z tables, t tables, and then we'll also have chi-squares coming up in the future. But so that's not a problem, but it is kind of nice to know how this calculator works. And different calculators work in different ways, and this ALEKS calculator is pretty easy to use. It's just that it only shows up on some problems and mainly on the interactive side of ALEKS. So I'll probably do some problems on the interactive side using a screen capture. I wish I could do that with this iPad, but I can't. At least I can't yet. I don't know how to do it, so I'll have to just do it with a mouse, and the writing isn't as good. Well, the writing's a little sketchy already, but with a mouse, it really goes downhill fast. So I hope this helped out, and I will sign off. I hope everybody's doing fine, and take care. Talk to you next time.